A mathematician is a device for turning coffee into theorems. Paul Erdős. Welcome to the Calculus Cafe, where the coffee is hot and the math is even hotter. I'll be your tour guide to this conceptual caffeination, and so let us get a cup of some inspiration. Doesn't appear to be anyone around. Hello? Is there anyone here? This is weird. Oh man, I could really use a cup of coffee right now. Hello? Are you open? Ah, here we go. Today's special. Complimentary cups of coffee. So here we are offered two types of coffee cups that fit snugly together, one bulging outward, the other bulging inward. As I decide which cup to go with, my mathematical brain kicks in and wonders which cup of coffee holds more. The hostess tells me they hold the same amount of coffee, but I can't have any unless I calculate a few things. That is, if I calculate how much coffee the cup holds. You observe that both cups are a surface of revolution. So what is a surface of revolution? Well, the simplest solid of revolution is produced by rotating a rectangle about an axis connected to one of its sides. The rotation produces a cylinder by volume. So what is the volume of a cylinder? Well, to get the volume of a cylinder, we take its base area and we multiply by its height. That is, what is the shape of its base? Well, the shape of its base is a circle, and a circle's area is pi r squared. That is, pi times its radius squared. Therefore, its volume, being equal to its base area times its height, is V equals pi r squared times h. Now, if we think of stacking disks on top of each other, we can get a sense of how integration will be used to calculate the volume using the disk method. So given any curve in the xy plane, one can think of slicing it up with rectangles, the area under that curve, and three-dimensionally thinking about rotating those rectangles around to make the disks that we will be summing up using integration. And we'll integrate along the axis of rotation. volume equals the integral from a to b of the area multiplied by dy, which represents the differential height of each cylindrical disc. One can imagine using this method to generate some very unique volumes. Here's one I made with a sinusoidal curve, and by rotating it about an axis, we get the petals and the bulbs of a sinusoidal flower. So this method will be perfect for us to generate the volumes and the solids that represent the cups of coffee in our problem. And the radius will be given by a function with respect to y, and we will differentiate along the y-axis. The disk method being given by volume is equal to the integral from a to b of pi times the function f of y squared dy. So let's unpack this idea just a little bit. We will begin with the cross-sectional areas of our cups. We will rotate one about the x equals 0 or y-axis, and x equals some value k. The curve that fits between the two cups, we'll call that x equals f of y. And that'll be the curve that we rotate about the axes to generate both cups. So let's just see what this will look like in 3 dimensions. Our first cup, when rotated, will generate the solid that is the cup bulging outward, and when we rotate the second one, we'll get the cup bulging inward. If we were to do this simultaneously, we get both cups fitting snugly together. Here it is from a few perspectives. Okay, so now that we have a basic overview of what we're doing here, let's examine the first cup a little closer. Volume A, cup A, will be given by the integral from 0 to h of pi f of y quantity squared dy. Cup B will be given by the integral from 0 to h of pi times k minus f of y quantity squared dy, and that is because our axis has been shifted away from the y-axis. Now our first task is to find the value of k that will make both cups have equal volumes. So let's scratch this out on a piece of napkin here. Alright, by setting the two volumes equal to each other, first we're going to expand out the integrand of the integral on the right hand side. And that's going to give us k squared minus 2k f of y plus f of y squared dy. And we can move some things around after we use linearity to distribute that integral and cancel a few things. What we discover is that by solving for k in this integral and using a1 to represent the area that is being revolved around the axis, k is equal to 2 times that area divided by h. And that area divided by h is the average value of f of y on that interval from 0 to h. So k is twice that value, and that will make both volumes equal. Brewing up a little conjecture. Here's the conjecture. If both cups of coffee have the same volume, then their cross-sectional areas will be the same. So we start off with VA equal VB, and the integral for the volume on the left we substitute in, and the volume for the integral of cup B we substitute in as well. What we discovered was that when we make these two integrals equal to each other, K is equal to 2 times the first area divided by H. Now the area of that rectangle of the two areas together is K times H. The area of the rectangle length times width is K times H. And that area is equal to the sum of area 1 and 2. Therefore we may substitute A1 plus A2 in for KH. And therefore we get A2 is equal to A1. Both areas are the same. Conjecture proven. The cross-sectional areas are equal. To finish our investigation, we will use some measurements that we know for regular coffee cups. The average coffee cup has a height of 8 centimeters, and our bulging coffee cup has a top radius of 3 centimeters and a middle radius of 4 centimeters. So we can model the curve that will rotate about the axis using a parabola. And a few coordinates given on this parabola will allow us to generate the function f of y is equal to negative 1/16 y minus 4 quantity squared plus 4. So now we can write out the volume integral from 0 to 8, a height of 8 centimeters, pi times that function squared dy. And that'll just require us to go through a little bit of the algebra to simplify that integral. So let's go through it. First, we'll simplify the green integral in there by multiplying things out and getting the quadratic. And then we're going to square this quadratic and write it out in expanded form. Carefully going through each term, and then of course when we integrate and put the limits of integration, when we put 0 in, the whole thing will go into 0, and then once we put 8 in, this is the expanded answer that we will get and have to evaluate. Taking this answer and multiplying through by pi, we get 340.12976 cubic centimeters. And if we convert this to US fluid ounces, that gives us a coffee cup holding coffee of 11.5 fluid ounces, just under 12 fluid ounces of coffee. So now we can order our coffee and enjoy. And I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.